We're very glad to have Sandip Trivedi, and he's going to tell us about the dynamics of near-extremal black holes. Before we start the talk, I just remember there's an announcement at 12 o'clock. There's a photo session outside for the participants this week. So please just be around at 12 o'clock. Okay, over to Sandip.
Thank you. Okay, so, good morning, everyone. Let me begin by thanking the real organizers for putting together such a nice meeting and giving me an opportunity to speak today. Last week we had some really beautiful and inspiring lectures by Juan Maldacena, which I think really set up the meeting. And actually they provide the context for what I will be talking about today as well. Although, of course, what I tell you is only a small footnote to, the entire beautiful set of developments that Juan surveyed and has led in many ways. So, but I'm kind of excited about this, and I hope you'll find it of some interest. Now, I opted for a blackboard talk, but I hope that works. So let me just check. I mean, is this too small for people in the back? I don't know. It's too small. So everything should be about this size, lettering-wise, you think? Okay, in between. Okay, sorry about that. I'll try to write bigger. So, so the title of the talk is The Dynamics of Near-Extremal Black Holes. And I'll begin with an introduction where I'll give you some motivation and some background. Then I'll describe a four-dimensional calculation. The conclusions we'll come to about the dynamics of near-extremal black holes are quite general, I believe. They're true in various dimensions, 4 and higher in particular. But for concreteness, we'll focus on one case, which will be an asymptotically anti-de Sitter space in 4 dimensions, and I'll describe that calculation for you. Since in this talk we will probe the dynamics in the spherically symmetric sector or the S-wave sector, the black holes to begin with we consider will not be rotating. They'll be charged non-rotating black holes, so they'll be spherically symmetric. We'll probe that dynamics by sending in stuff also in the spherically symmetric manner. So that will be the entire talk for today. And therefore, it will be quite natural to try and understand the 4-dimensional calculations from a 2-dimensional perspective obtained by dimensional reduction. And what we'll find is that quite generally, the 4-dimensional system will map to a well-known 2-dimensional model of gravity, the Jakiv-Teitelbaum model, with corrections. But we'll argue that for the purposes of interest, the corrections are not important at low enough energies and close to extremality. So in fact, quite generally, the model will map to the Jakiv-Teitelbaum model, and conclusions we come to about the dynamics of near-extremal black holes will be therefore quite general and will be in agreement with what is already known in this model. And that's sort of, in one sentence, one of the key points of the talk. And I'll tell you more. And then we'll end with conclusions. Okay, so that's the outline. I'll just tell you a little bit about some of the references. The work I'll describe is done along with various students and ex-students of TIFR, Pranjal Nayak, Ashish Shukla, Ronak Soni, Vishal, who's here in the audience, and is written up. I'll also briefly tell you about what happens when you go beyond the spherically symmetric approximation towards the end of the talk. This is work still in preparation with Upamanyu Moitra and Vishal. Upamanyu is also here in the audience. Now there's a huge body of literature, the original work of Jakiv and Teitelbaum themselves, the paper by Almiri and Polchinski, recent beautiful work by Maldacena, Stanford, and Yang. All this will also map to the SYK model, on which there's a huge literature which I don't write down. And there was already a very nice talk in this meeting by Gautam based on the work that he has done with Gaikwad, Joshi, and Spenta, and Lata Joshi and Spenta. And I think one of the collaborators is also here, perhaps, besides Spenta. So, okay, that is also a reference. Okay, and I'm sorry, it's not by any means a complete set of references. Okay, so let's get going on the introduction, and I'll try to write big enough. So the study of the low energy behavior of extremal and near-extremal black holes and black brains has been a very rewarding subject in our field, as you know, and especially for black brains, extended objects. A very beautiful story has emerged and been very important and is at the heart of the ADS-CFT correspondence. Namely, if you take extended black brains, say D3 brains, and you want to probe, this is in asymptotically flat space, okay, and you want to probe them by sending in, say, gravitons from infinity at low enough energies, then we know there's a very nice effective field theory which describes the dynamics of the black brains interacting with the probe fields, and that is, say, for D3 brains, n equals 4 super Young-Mills theory. Okay, and so this is from the perspective of the full geometry, a low energy effective theory, but we know that in fact the effective theory is a sensible theory, consistent theory in its own right. Okay, it's you don't need to just view it as an effective field theory, and in fact it then describes the dynamics of gravity in the near horizon region, which is ADS 5 process 5. So in this case, and in many such cases, as we know for extended brains, you have an effective theory from the point of view of, say, asymptotic infinity, which describes the dynamics, low energy dynamics, but in fact it can be promoted to a full theory. So it's actually even more powerful kind of equivalence. All right, what about black holes? Extremal or near-extremal black holes. This already came up in the talk of Jan's yesterday. Here the situation has been more, in a sense, interesting. Okay, so these are not extended objects. They are, if you like, point-like or with finite-sized horizons. It is known that many extremal black holes have a near-horizon geometry which again has anti-de Sitter space. And say if we were in 4 dimensions, would be, for example, ATS2 cross S2. And we now know that this near-horizon geometry is good for understanding all the ground state properties of these extremal systems. And beautiful work, as you know, by Sen, Ashok Sen, and Dabholkar, and various collaborators. There's now a quantum entropy function formalism which allows you to compute the ground state degeneracy, not only to some leading order in charge, but actually even with exponentially small corrections. So this is a beautiful story that's quite well known and understood by now. But when you start trying to go away from extremality by exciting the system a little bit, then things get more interesting and more complicated. And one thing which one can show, it was shown, I think, in a very nice paper by, I think it was known widely, but in particular was shown in a nice paper quite a long time ago by Michelson. Michelson, Maldacena, and Strominger, is that when you excite the system a little bit, then, by turning on some perturbation, then this system is unstable. And the physical reason for that is very simple to understand. The transverse S2 here has some fixed finite size, so that the perturbations don't have anywhere to go to dissipate themselves. Okay, unlike in flat space, say, where you can go to asymptotic infinity, the radius of the sphere grows, and the effects dissipate themselves. Here, this radius is finite, so the effects of the perturbations don't dissipate, and in fact, they grow. This is what was shown, rendering the underlying geometry unstable to even small perturbations. So therefore, when it comes to studying the perturbations, it seems more or less clear this geometry by itself is too drastic a truncation. You need to include at least some corrections that will allow the S2 to grow in size. Okay, that was sort of at least what was physically clear, but what form does that effective theory then take, which captures the dynamics in a consistent way for at least low energy excitations of this extremal system? That was not very well known. Okay, so for small perturbations we need to go beyond ADS2. But what is the effective theory? This was not very well known until recently, when, in two ways, there have been very interesting developments that have come together. And one sort of, as you all know, one path came through condensed matter physics and so on, and was the study of SYK and related models. So I'll just call them SYK-like models, I guess. And there's a lot of literature on this. And the other was this paper building on the work again of others by Maldacena, Stanford, and Yang, who studied the Jakiv-Teitel-Boehm model. This was the analysis in 2D gravity. And what was found here was this model has a ADS2 geometry, and what was found was that there was a very sort of nice effective field theory which governed the dynamics of this model when you probed it, say, with probe fields, all right? And that theory involves the dynamics of time reparameterizations, which I'll describe to you. What I mean by this described by a particular action which involves the Schwarzian derivative of these reparameterizations. So I'll just call it the Schwarzian derivative action, or the Schwarzian action for gravity as we go along. Okay? So the kind of behavior which was seen at low energies in the SYK model was reproduced in this theory of gravity, and it involves basically an action which arises due to symmetry considerations. Now that's a very interesting and beautiful situation, because oftentimes if you get an effective field theory and it's arising from symmetry considerations, you think that it should have much greater validity, that in other situations where the underlying microscopics or the underlying full description could be quite different at low enough energies, the same symmetry considerations will apply and you should get the same low energy dynamics. And in fact, that is what we will find today, that for a very large class of systems, in fact, the low energy dynamics is governed by exactly the same symmetry considerations and the same kind of action. Therefore, these conclusions that were found are actually very general. And so we now understand in many, I would say, systems of near-extremal black holes, what is the effective field theory for low energy excitations, okay, going beyond just extremality. Okay, now there is one caveat in what I will say today. So let me just say that, but let me just write this down. So, so the main result is actually, now there's one important caveat today, and we are trying to go beyond that. If you ask me, although it's a little tentative, I think the conclusion will be even more general. But the main caveat is that today we will look at only excitations which are spherically symmetric. Okay, that's an obvious place to start if you're trying to see whether the conclusions which come from 2D gravity hold, all right? But in fact, I suspect that they are more general, as I will try to indicate towards the end of the talk, okay? So what we will show for today is the following, that at least in the S-wave sector, that is for spherically symmetric situations, and this is a consistent truncation, the effective theory for... Now, again, to be specific, we'll consider a particular type of extremal black hole, but the conclusions, as you will see, are quite general, and this will come out from the analysis. The effective theory, so let me just not qualify that, is described by the same Schwarzian theory. Yeah. Okay, that's the main conclusion. Yeah, sorry, I should have said that. S wave here means spherically symmetric.
Sandip, so does this mean in the dual field theory that you start with presumably a three-dimensional field theory, there will also be a truncation of that field theory which will, to some quantum mechanics whose low energy will be described by this? Is that something one can explicitly do or see?
Well, that's exactly correct. What's very nice about this general result is that we have so many microscopic theories. For example, in string theory, where you get extremal black holes. And, you know, what this shows is that there should be the Schwarzian dynamics at low energies, at least at strong coupling in all these situations. Now, that opens, we haven't done the analysis microscopically at weak coupling and then trying to take it at strong coupling to see whether this is true or not. But all that opens up. So it's not just the SYK model. You know, there will be models which arise from string theory where these conclusions are true. So that's one of the reasons why it's sort of exciting. Yeah.
So, Sandip, what is this effective theory supposed to describe? For example, if there are additional fields in the bulk, let's say the kind of things that this MIT group studied, Faulkner and Hong Liu and so on and so forth, McGreevy. So where they probe it by they probe ADS2 by a fermionic field.
Right.
That kind of a thing is the statement that you should couple to that fermionic field to the Schwarzian and get out. I mean, what is the...
That's exactly correct.
What is the domain of this? So it is supposed to capture that kind of thing?
It's supposed to capture that kind of thing. And I'll describe the calculations we do more concretely so you'll see. But that's exactly the point, that you have some external probes. And those external probes are the analog of sending in gravitons from asymptotic infinity. You know, those translate to couplings that you turn on the boundary here. And the response of the system to those probes is captured by the Schwarzian theory, quite generally. And that's exactly what you'll find. What McGreevy et al. Did was just 2-point functions, but here we'll go beyond 2-point functions where the fields are no longer free, and then the resulting interactions will be the Schwarzian. Exactly. Okay, so that's the point. I'm going really slowly, so that's okay. I just wanted to state the main result. I'll give you a little bit of detail now. So we'll focus on one concrete case, and this is asymptotically ADS4. Okay, and the reason we looked at asymptotic ADS geometries is there we have the beautiful holographic dictionary, say, of ADS4 to guide us, okay, in the calculations we want to do. So we are going to turn on some probe at the boundary of ADS4. That'll translate to some probe, if you like, at the boundary of this ADS2 or near ADS2 region. And we'll compute correlation functions, etc., to probe the whole system. Okay, so this is a good crutch to have. I should have emphasized here that I sort of said it, but let me say that this dynamics is crucially tied to the fact that you don't have exactly ADS2, but you have near ADS2. So the corrections are very important for how this dynamics arises, and that'll be true for us also. Now, what's the geometry? So, and we look at a very simple system, which is the simplest context where you can get a extremal system, I would say charged extremal system. And I won't be careful about coefficients and signs here. So we have gravity, we have a negative cosmological constant to get ADS4, and we have a gauge field. And as you all know, this system has charged black holes. So they have Reisner-Nordström black holes. And in particular, there are extremal or near-extremal black holes of this type, and those will be the ones we look at. What is the geometry of these black holes? They're spherically symmetric. The geometry is described by a metric like this. So there's an S2. This, in some standard coordinates of the type I'm choosing, can just be taken to be the radial coordinate. And there's a gravitational redshift. That redshift goes to 0 at the horizon, and so on. And so schematically, the geometry looks like this. You have a long throat where the geometry is approximately ADS2 cross S2. And then that opens out asymptotically to ADS4. Okay, and let's say this radial coordinate is growing in this direction. So that's the geometry. There's some very simple metric. The horizon for the extremal black hole will be located in the extremal case, will be located at R equals, let's say, RH, and therefore the entropy will go like RH square over G Newton. So RH is an important parameter from the point of view of, all right, I should introduce one more parameter, the radius of the ADS4, which will be L. The radius of the ADS2, which you get, is related to L, but it's something like L over root 6, all right, doesn't matter, which we'll call L2 sometimes. So basically, of some radius, it becomes smaller as you expect on general grounds to some slightly smaller radius in the ADS2 region. Okay, and the parameter RH corresponds in the boundary field theory, which is dual to ADS4, to turning on a cosmological to turning on a chemical potential, which is related to RH by a relation of this type, okay, which is what you would expect from radius energy duality or whatever, that, yeah, L square is 1 over lambda, whatever. So basically, as you charge the system up more and more, you give it a bigger and bigger chemical potential, then this radius at the horizon grows more and more, and the scale RH becomes bigger and bigger. Okay, the boundary of the system, I'm working in global coordinates here. The boundary of the system is S2 cross time. That's where the boundary field theory lives. Okay, so that's the system. Now, we'll be interested near extremality. At extremality, the temperature goes to 0. Near extremal, the temperature is small compared to what? The only scale in the problem, which is the chemical potential. You have a boundary conformal field theory. The only scale is being set by the chemical potential. So we are going to look at temperatures very small compared to mu. This is a very, very interesting fact about ADS black holes, that let me put it, I'm going to look at large black holes here. I'm going to look at, yeah, that's why the intuition from, I should have said that, thank you. Just for simplicity, we can look at a general black hole, but just for simplicity, I'll look at large black holes. Where the radius is very much bigger than L. Okay, and for those black holes, this is true. Otherwise, you go over into the flat space intuition. That's right. That's right. Okay, so all right, we look at temperatures very much smaller than mu. What do we know about the system? Well, the thermodynamics is easy to compute. The entropy is the ground state entropy, which is tied to the degeneracy plus a correction. Okay, and that correction is linear in temperature with some coefficient.
This mu, is it really the chemical potential that couples to the charge, or is that beta mu? I mean, sometimes people use beta mu couple
It's
to
really the chemical potential.
So there's no factor of beta.
Sorry?
So there's no factor of beta that.
There's no factor of beta. You can be at beta equal to infinity, which is the extremal limit, and yet, the system has a chemical potential, it has a charge, and mu is that chemical potential.
And also, where is approximately at what value of R is there a boundary between the ADS2 and ADS4? Are you going to explain that?
I'm going to explain that to you, but basically, let me say it now, that what we'll find is that there is this effective field theory which governs the dynamics of the near horizon region, and that effective field theory can be thought of as living in the near ADS2 region, which is cut off by a boundary. The dynamics of that boundary is where all the non-trivial physics will arise, but roughly it will be located at some cutoff scale, let's say, RC, and this cutoff scale will be such that RC minus RH, let me just say one more thing and then this will become clearer. I'll say it now and then I'll try to explain it, that the RC minus RH over the scale RH has to be very much less than 1. Okay, so, roughly in this geometry, in these coordinates, as you move out in the radial direction, you're going to higher and higher energies in the CFT. Okay, the radial location R of order RH is of order the chemical potential. All the dynamics which occurs at energies or temperatures much lower than the chemical potential lies to the left here, in the region of greater gravitational redshift. And the effect, and the screen will be located deep in that region. Okay, how deep can you locate it? That depends a little bit on the energy you are probing. Basically, the energy that you probe the system with, let's say you have a temperature, the temperature corresponds to the horizon now being located here. The throat, which is infinite in the extremal limit, comes to a finite distance. You can then locate the screen sufficiently far from the horizon, okay, in an increasing direction, but much located at a radial location much less than where the chemical potential is. And that'll be the general story. As long as you locate the screen there, exactly where you locate the screen will not be important. This is always the way effective field theory works, right? You got to put in a cutoff, but if you put the cutoff at an energy high enough compared to where the energies of interest lie, it doesn't matter exactly where you place the cutoff. That's why you get away with effective field theory. It'll be exactly the same here. So that's where RC will be located, so this will be much less than 1, and it has to be located so that, I won't make that precise here, so that the screen corresponds to a location which is much bigger in radial value than the energy scale of interest. Okay.
So the S2 radius is always RH, right? But the ADS2 is the one that yours.
That's correct. That's correct. That's correct.
Is that right?
That's correct. Yes. Let me just write the metric. So that's exactly correct. The ADS2 radius for a big black hole is of order L, but the S2 radius is RH. So as the chemical potentials increase, the size of the S2 increases, the entropy increases, and so on. That's right. Okay. All right, so the first thing is that the thermodynamics is linear in the temperature, and what we'll try to do here is not only explain the thermodynamics, which has been thought about quite a lot, but in fact probe the system in a much more delicate and quantitative manner, which is that we will subject the system to probes, as came up in the question with Loga, and compute correlation functions and try to ask what kind of an effective theory will reproduce those correlation functions. Okay, so what we'll do is we will add, as the simplest case, an additional free scalar field, free except for its gravitational. And we'll throw this scalar field in, pulses of the scalar field in a spherically symmetric way, and look at the response of the system. All right? So that's what we'll do. So besides thermodynamics, we look at response to probe scalar field. And what we will find, as I was saying, that, that for both of these, okay, getting the thermodynamics right and the response, in particular the 4-point function, I'll tell you why the 4-point function is worth looking at. For getting both of these things right, the Schwarzian theory will be good enough. All right, and once you see the analysis, it'll be clear that for higher endpoint functions also, that'll work. Okay, and yes, I think the answer is yes, in that the zeroth order absorption is just free propagation. You know, if you just had the extremal black hole and you throw something in, there's a transmission and a reflection probability. And just the 2-point function in ADS2, when you think about it correctly, should encode that information. Just as the 2-point functions in ADS3 or 4 correctly encoded the absorption from black vanes. It's not something I was meaning to do, but I haven't done. I think that'll come out right. What the Schwarzian theory gets in addition is the additional interactions which arise due to gravitational dynamics, away from the free. And so the corrections that arise for absorption and transmission there is what the Schwarzian theory gets right. Both of these, that is the thermodynamics. It's both of these aspects correct. Okay, so when it comes to correlation functions, what are we doing? Here is the black hole. We are sending in pulses, okay, of the scalar field. The scalar field is free except for gravitational interactions. But you're in the S wave. There are no gravitons in the S wave sector. Okay, so you might ask, what kind of interactions are we talking about? And the answer is, even though there are no gravitons, there is gravitational interaction. Just as in QED, if you had spherically symmetric charge distributions, there's still a Coulomb interaction. Okay, and that changes the energy and so on. So also in gravitational systems, you do have this analog of the Coulomb interaction. And that is the interaction which is non-trivial, which affects higher point, which is why the higher point correlations are non-trivial. And that is the interaction, this Coulomb-like interaction, which the Schwarzian theory gets right. Okay, so, so even in S wave, there are non-trivial gravitational interactions which the Schwarzian theory captures at low energies. Okay, so that's the physics of what one is getting right here. And the 4-point function is the first time you see these interactions. The 3-point function in the system vanishes because there's a phi going to minus phi symmetry. And so, and the 2-point is just free propagation. That's why the 4-point is one where which is worth starting with. And once you get that right, it's clear how to get the higher point correlators. Spenta, please.
So, so suppose you're not scattering an S wave, and you have some other higher harmonics. So you think that this 1 degree of freedom of the Schwarzian can still capture the effective dynamics?
Yeah, so
all
this is
features of the effective dynamics.
This is work in progress, and up to a minor caveat, I think, which will work out, which I can tell you more about, I think the answer is yes. And the reason is the following. At low energies, as you know, there's a contribution in the JT model, which is enhanced by this coupling J. You know, the analog of that coupling here is the radius of the horizon for us. Okay, and the leading contribution, therefore, goes like, in our units, RH to the 3rd power. There are various contributions which are non-universal, which go like RH to the 2nd power. But this RH to the 3rd power, we find, only arises from the Coulomb interactions. And it dominates at low energies over the RH square interactions. That's why I think the conclusion will be more general. But there's a bit of a caveat. One last step we are still fully sorting out. And I'll give you the argument in general why you might expect towards the end. Okay. Okay, now I'm down to 20 minutes, which is good. So, so that's what we find. Now I'll describe the calculation just a little bit to you. So I'm really done with the intro. I want to now describe to you the 4D calculation. This is a calculation which won't assume anything about the near ADS2, about setting up some screen here and attributing any dynamics to that screen, etc. This is a calculation we'll do as per the standard rules of holography in ADS4. We'll do that calculation. We'll then take its low energy limit and we'll get an answer. Okay, that'll be second part of the talk, the 4D. And then we'll see we get exactly the same answer from the dynamics of the near horizon region due to a fluctuating boundary. Described, this boundary will fluctuate, described by the Schwarzian action. That'll give us the same answer. But this was somehow not obvious to us, but it's a straightforward calculation to do. So the calculation is the following. So this is the geometry, as I was describing, the extremal geometry. This is the ADS4 region. And the probe scalar corresponds to operators, scalar operators in the dual theory. We can think of a 4-point function, say, as 4 insertions. And so we insert these operators. They are spherically symmetric configurations, so they only depend on time as far as the boundary theory is concerned. Since the boundary theory lives on S2 cross time, okay? And then we look at the resulting dynamics. We take the energies of interest, which is inversely related to the time intervals, to be very much smaller than mu. And if we are looking at a near-extremal system, not exactly at extremality, we take the temperature also to be much smaller than mu. Okay? All right, well, what happens? If you had genuine gravitons, we could draw the following type of diagrams, bulk diagrams. The exchange of some graviton in the middle, all right? And as you increase the time interval between these points, we expect, and you can show that from the explicit calculations, except for contact terms, which is a subtlety I won't go into. If you look at the non-contact part of the 4-point function, that the contribution comes from further and further in the interior. So roughly speaking, these bulk to boundary propagators go deep inside, and the graviton gets exchanged deeper and deeper inside as you go to lower and lower energies. This is just a general fact which you can show. The position space correlator, by energy I mean where delta t is of order the interval between the insertions. So as you make the interval much bigger compared to the chemical potential, then this is what you get. Correlator goes deeper and deeper inside. Now we don't have genuine gravitons. We only have this Coulomb dressing, and that's part of the subtlety of the calculation actually. If there were genuine gravitons, it's in a sense easier to do because this Coulomb dressing can easily be lost for some gauge artifact and so on. So you have to be very, we had to be a bit careful about it. But anyway, even though there are no genuine gravitons, the same pictures is there. Okay, when you set up the 4-point function using bulk to boundary propagators or in whatever way you want to, you find that except for contact terms, all the contribution comes from the region which is in the ADS2 cross S2 part, near ADS2 cross S2 part. We are in S-wave. If you're in the S-wave sector, this object which is exchanged would have to have no angular momentum, no spin 2 could be exchanged. Yeah. And that complicates things. That's why when we go to higher harmonics, it's actually easier to make some of the arguments, in a sense. Okay, all right, so, but this feature still survives. So the contribution comes from the near horizon region, and that contribution, I'll write down now the answer, can be thought of as follows. There are 4 of these probes. 2 of them come together to give a stress energy tensor. So you have 2 stress energy tensors, and then you have some gravitational interaction, okay, which dresses them. All right, and so the 4-point function can be read off from the on-shell action subject to suitable boundary conditions corresponding to the insertion of these operators, and that on-shell action has two stress energy tensors, each of which is factor of stress energy tensor contains two factors of the field. So that's why it's a 4-point function. And it looks like this. Let's not get into details. This is a G Newton because it's a gravitational interaction. And I'm writing it in terms of a bulk integral here. And there are a few different kinds of terms. But importantly, there is the radius of the horizon to the third power, which comes out. Okay, and that's important. And then there's extra stuff which cares about the gravitational redshift, a square, etc., etc. I won't write all of that out here. But okay, just to show you that we did some work. This is TR, I think. Okay, never mind. Your factors stress energy tensor with some components. Don't be worried about the 1 over TR because we are actually doing it in frequency space is what we do the calculation in. So these are actually powers of frequency. You've got some expression. You can obtain it very explicitly because after all, there are no genuine gravitons. This is just some Coulomb dressing. So the calculation is trivial to drive through. And the important thing I want to emphasize here for the purposes of this talk is that this effect goes like in suitable units. Wherever the units aren't making sense, I've set L ADS equal to 1. So we can put that back in, but it goes like RH cube. Okay, that's how the answer goes. All right, okay, so this answer can be obtained. And so we know the correct answer here just on grounds of what ADS4 holography tells us. It goes with the volume, but actually the power is kind of important. The reason the power is interesting is the following. If you just did Kaluza-Klein reduction, which we'll do next, the radius of the S2 goes like RH. So the volume of the S2 goes like RH square. Okay? Okay? So you might have thought that the answer should scale like RH square. But it's... Sorry? Yeah, goes like RH square. Yeah. So you might have thought that the prefactor goes like RH square, but it goes like RH cube. And therein lies the whole story, okay, as to why the Schwarzian action dominates and so on, which we'll come to in a moment.
These effectively 3 frequencies, right? Because there are 4 insertions and there's 1 momentum conservation, so 3 frequencies. So I don't see where the answer. So you'll need to compute also the 4th, the quartic terms.
Yeah. So each of these stress tensors is, some expression like dr phi, dr phi.
Oh, I see.
And so you got 2 powers of phi here and here, so there are 4 phis. And these phis have to be obtained by solving in the bulk for the phi field subject to the boundary conditions. In other words, they are bulk to boundary properties.
So this is not the boundary stress tensor. This is some bulk stress tensor.
Sorry. This is a bulk integral. This is the bulk. Scalar field stress tensor. Later on, this answer can be also beautifully written on the boundary, but I'm just in terms of boundary quantities, but I'm not doing that.
Of 3 frequencies, which you've calculated, omega 1, omega 2, omega 3.
3 frequencies and the sources at those frequencies. And the 4 sources that you turn on.
I was thinking of just computing a correlation function, but you could also, fine.
Yeah.
And, right, so.
Yeah, that's right, okay. Then it's just the 3 frequencies. Okay, let me just go on. So you get my only point is that, what the answer should be is not in doubt, and it can be obtained. Okay, now let's try to see how to obtain it from, since the bulk region which is contributing is also in the ADS2 cross S2 or near ADS2 cross S2 region, we'll try to obtain it from that region more in terms of a 2D description. So that's the third part of the talk. Okay, so let's do the dimensional reduction. Since we are working with spherically symmetric configurations, as I said, it's easy enough to reduce the theory. So let me use this notation. Phi square is just the radius of the two sphere. Okay, so and x and alpha and beta go over time and r, if you like, or yeah. Okay, so that's why we plug it in. We do some changes in frame and so on and so forth, which I will skip over. And here's what we get as the action. The action we started with, I really should have put a 1 over g Newton there. I'm sorry I didn't. But we start with has a 1 over g Newton. Okay, and so here what we get has got an RH square over g Newton. There's a topological piece which, won't do very much. This is now in 2D. This is the boundary in 2D. So this part is just topological, total derivative. And then there's interesting stuff. I'm going to write capital phi as phi naught 1 plus little phi. This phi naught will be RH, the radius at the horizon. Okay, the little phi will be the fluctuation about it. This involves little phi and 2D curvature. Then there is a some boundary terms which involve little phi. And then there are important corrections which are quadratic in phi. So this part is topological piece, linear in the fluctuation of phi, and then there are terms quadratic in phi, both on the boundary and in the bulk, which I will sort of indicate because we won't use them very much. Sorry about getting so messy. Okay, so important thing is there are linear terms in phi, there are quadratic terms in phi, and then there's a topological piece. Okay, this is a power series in phi. So when you go to further powers, you're going to get additional powers. Okay, but okay, we'll see why it's for the region which is deep inside. This will be good enough. Corrections due to the higher powers will be also.
Sandip, I have a question. What happened to the electromagnetic field?
Yeah, the electromagnetic field is not propagating in the S-wave sector. So you can either do an electrically charged black hole or a magnetically charged black hole. Conceptually, it's actually easier to do the magnetically charged one, but you get the same answer. You can therefore solve for the electromagnetic field in terms of the metric using the Gauss law and put that back in, then the dynamical degrees are only there. Okay, so we get an action like that. If you look at what the action for the JT model is, the action in the JT model is all the terms which are linear, okay, without the quadratic pieces. Okay, that's the JT model. So you get something which is approximately JT but with corrections, and it turns out that, bad, no? Sorry, should I write it again? Sorry. I thought just the handwriting was already bad, so I was wondering that I should write it. Is that any better? Should I just rewrite the whole thing? Okay, there are linear terms, there are quadratic terms. The linear terms are the JT model. The quadratic terms are corrections. And it turns out, actually, that the quadratic terms cannot be neglected to the order we work in general. And let me tell you why, just for a moment. What the linear terms here do, in general, is that they allow... Let me just go back to this solution. The solution was that b square went like r square. So if I were expanding this about the horizon, I could write this as RH plus some variable delta r square, where delta R is R minus RH, and therefore it would go like RH square, 1 plus 2 delta R over RH. Okay, and the variable little phi is the fluctuations in the radius of the S2. So you see, as you keep the corrections from ADS2, you're going to have the radius change. And in terms of the physical motivation I gave you to control the back reaction, etc., that's important because it's the growing radius that will allow the system to have sort of a stable response. So this growth is important. These deviations from the ADS2 geometry are important. Just 1 second, I'll complete. Now, besides the geometry, the radius of the S2 departing from its value at the, at the horizon, the geometry also in the NARP will depart from ADS2, and those departures are of the same order. All right. So if I were to write down A square in the near horizon region, then these would go something like R minus RH square over L2 square. So the metric, if I wrote it, would be 1 plus something of order Okay, so there's an ADS2 part and there are corrections. The corrections are again of order delta R over RH. Okay, they're of the same order as these corrections are. Okay.
By beta over, by some factor of T over mu.
Here I just did the extremal black hole. And then if you like, you can heat it up, but it doesn't change the basic story.
Isn't that important, the fact that it's near-extremal?
So, the whole issue can be studied just at extremality itself. You can do the scattering at low energies compared to the chemical potential. You can ask, is there an effective theory that governs that? And you could do it at a small temperature also. You make the temperature direction periodic or not, that's the difference, but the effective action is still the Schwarzian action. Yeah. It's more that you're keeping not just the exact attractor region, that is the horizon region, but the near horizon region, where the corrections from ADS2 cross S2 come in. That's why you're keeping this. And that's actually important. To work with the near ADS2 region is actually important in getting the Schwarzian action and in getting this RH cube behavior we saw. If you want to get that behavior, you'll have to keep that correction that will turn out. So that's why we are doing that. Okay, so you have corrections at the same order in the two-dimensional metric as you have corrections in the radius of the S2, and these corrections are generated from the quadratic terms. I won't quite explain that, from the quadratic terms in the action. So these terms are actually not non-negligible, to the same order as you want to keep deviations from the ADS2 cross S2 geometry. However, it turns out that for the response of interest for us, okay, these terms can be neglected. They give sub-leading contributions to the leading response which we calculate. All right. So this can sometimes happen that there are two effects of the same order, but then when you end up computing, say, correlation functions, etc., they don't end up contributing. I don't know. That is the case here at any rate, that these can be neglected. That's something that wasn't obvious to us till we set up the system and the analysis was done, but it turns out to be the case. So therefore, in the end, although the model doesn't quite dimensionally reduce to the Jekyll-Teitelbaum model, okay, for the leading order behavior of interest at low energies, the deviations are not important. Okay, and or maybe I should be able to say that with a little more insight, but let me try to say that with a little more insight in a minute. Okay, so I'll try to say that better. Behavior of the correlators, additional terms, quadratic, and other powers, sorry, I'll end soon, etc. Little phi are not important. And the model really becomes the Jekyll-Teitelbaum model of 2D gravity. Now, why is it that these corrections are not important? I'll just try to explain that and then I'll stop. The physical reason is the following. The leading effect which arises due to the following. The fact that the dilaton, that the scalar, which I can call the dilaton, the fact that the scalar is evolving once I keep the leading corrections. So if I look at the deviations from the radius at the horizon, these deviations go like, let's say, I use this. They go linearly in this radial coordinate away from the horizon. The fact that it's not the value exactly at the horizon and you keep these departures means that if you now look at ADS2 with some boundary, so you say, let me try to describe the whole, let me try to arrive at the same results by thinking of some region of near ADS2 space. That means ADS2 space with some boundary. Then what happens is in the presence of this dilaton, which is no longer a constant, the fluctuations of this boundary now come with a cost in action, but a finite cost in action. All right? And the reason why this boundary can fluctuate with a finite cost in action is that the boundary is in ADS2 and it's of just one dimension and so on. So it's a one-dimensional object. Its fluctuations turn out to be of finite cost in action. And that the fluctuations of this boundary capture the essential dynamics which gives the leading RH cube contribution. Okay, and so the fluctuations of the boundary of ADS2, okay, this is what is described by the Schwarzian action. For this, keeping the departures from the horizon value for the dilaton are important, but the corrections in the other components of the metric which would have arisen from the additional terms we get, which are not there in the JT model, they're not important. Okay, and so these additional corrections will all contribute to terms which are sub-leading, not going like, say, the leading power.
Can I ask a question?
Yeah.
So Sandip, what is your boundary condition for the small phi field from the two-dimensional point of view?
Okay, I'm sorry I've had to skip over many details,
yes.
But the boundary condition, so where is the fluctuating boundary located? There should be a gauge invariant way to specify where it's located, and it's located at phi equals some value. Okay, so that's where you locate the boundary, some fixed value. You choose the value and you locate the screen, and then it doesn't matter exactly where you locate the scalar field, because this is the gauge invariant way to specify what is the cutoff in your effective field. As long as the cutoff is such that you are far away from the temperature or energy scales of interest, it doesn't matter where it's located. You get the same.
If I look at I'm just recalling Maldacena, Stanford, Yang. If I look at the Jakob-Teitelbaum theory and solve the equations of motion, I find that the dilaton actually has a divergence as you go to the... Right. That's what it's worrying me actually when you're
that divergence cancels out. So just very quickly, the dynamics arises from this term, phi times extrinsic curvature, up to some counter terms. And what happens is, this metric factor diverges, phi diverges, and k has a term which goes to 0. And those two cancel each other. So that the answer is finite and independent of where you located your dilaton.
You neglect the higher order terms. That's
the higher order terms give you terms which are either not finite in this limit or they are subdominant in RH, in 1 over RH. Yeah, it's either subdominant or they are down in 1 over RH. Okay, so there is a dimension. Okay, should have been a little better. I'll just say that in a minute. Corrections are subdominant, and I'll tell you in what sense now very, very precisely. What are the parameters which are governing this? One is omega, the energy is very much smaller than mu, okay? But there is one more parameter, which I should have been clearer about, which is tied to the scale RH, and that is that RH over L is very much bigger than 1. This is because we did the whole analysis for big black holes. There's a similar analysis for small black holes which I'm not doing here, where L Planck will enter and so on. But this is the analysis for big black holes. This means physically that the units I've chosen, the boundary CFT lives on a S2 of size L, okay, and it's got a chemical potential mu, and this means that mu times L is very much bigger than 1. All right, so that's the limit, that's the other parameter we work with. So it's small energies, large chemical potentials. In that, the Schwarzian action dominates, and it dominates very universally. Everything else is subdominant for one or the other reason. Yeah, we can talk about that more. So, okay, so let me just wrap up. So the conclusion is, and I'm sorry if some of the details didn't come through very clearly, but the conclusion is that quite universally, so the Schwarzian theory arises quite universally and dominates the low energy dynamics. And once you see it for the 4-point functions, there's a diagrammatic way to understand why it's true for all n-point correlators. The fact that it's universal, I think, is we've done the analysis, as I said, for big black holes in ADS, but I think it's actually quite generally true. But before that, let me say an important thing is beyond S-wave. And I think, this is going to go through there's a bit of a subtlety. There's a whole connection between the Schwarzian action and large gauge transformations and so on, which some of you know I couldn't go into. But beyond the basic reason why you expect this to go through beyond S-wave is the following. A particular 4-dimensional probe field, when you look at it from the point of view of ADS2 times S2, so if you have an ADS2 cross S2 like geometry, you have a 4-dimensional probe, you Kaluza-Klein decompose it on the S2. All the higher Kaluza-Klein harmonics correspond to more massive fields on ADS2. As the mass goes up, as the Kaluza-Klein harmonic goes up, the mass in ADS2 goes up. Okay, now correlation bigger mass in ADS2 means you have a corresponding operator with a bigger anomalous dimension. At low energies, just by scaling, the correlators of higher anomalous dimension operators are suppressed. Okay, just by power counting. So therefore, the low energy dynamics will actually be dominated by the S-wave sector. Okay, and that is why one expects, there are a few ifs and buts, but for that reason one expects that the S-wave sector will dominate at low energies, and the Schwarzian theory we've already shown is the dominant contribution in the S-wave. So therefore I would say probably, I might be wrong, but probably, still to dot some I's, conclusion still true. And of course, there are many other situations. We just looked at asymptotically ADS4, but it's really the fact that you get this ADS2 throat, which is important, I think. So this should work really, I think, also in asymptotically flat space, etc., etc. So the conclusion, I think, should be more general. And finally, and this point already came up, since it's so general, there are so many microscopic models in string theory which give rise to ADS2 extremal black holes. ADS2 cross S2 extremal black holes. And this conclusion should hold there as well. And so it becomes very interesting to ask, if you look at the microscopic theory for these situations, do you see the same phenomena there or not? Like they saw in the SYK model, do you see it or not? These are often quiver theories and so on. I just haven't gone down that route because we've been busy trying to dot the I's for this story. But I think that's very interesting, and that would be well worth expanding the whole investigation. So with that, I'll stop. Sorry to go over time.
So I have a couple of questions about this issue of the validity. I mean, so one question is, So in your original 4D action, you didn't include any massless scalars. Is that important? I mean, yeah.
Yeah, it's true that the probe I took, I rubbed it out somewhere. The probe I took was a massive scalar field.
Yeah.
And not a massless.
Yeah.
The reason was this argument that, I think it's because I got a bit confused, but this argument that as you go to lower energies, except for contact terms, what really comes out of the analysis when I was saying that the contribution comes deeper and deeper in the throat as you go to lower and lower energies, what actually the bulk, the calculation is that you fold in bulk to boundary propagators with not a genuine graviton, but the Coulomb dressing effect. And what really comes out is that up to contact terms, my statement is correct. You can show that. But there was some subtlety for the massless case which we didn't fully sort out. I think it'll get sorted out. But for that reason, I took a massive field.
But I mean, one might be concerned that in the presence of a massless scalar, the low energy effective action will not be Joukiffe-Teitelbaum. It'll be the massless scalar is not going to go away, or it doesn't seem clear that it's going to go away. Right?
Oh, okay. No, sorry, what I meant to say was the gravitational dynamics is correctly captured by the Schwarzian theory.
And that won't be ruined?
I don't think it will be. The massless scalar will couple in a way which we can determine to the Schwarzian modes, to the modes of time reparameterization. And then the full dynamics will work out in that way. So I'm sorry if I said that. What I really meant was the gravitational part of the interactions are captured by the Schwarzian action. And then the probe scalar is always present as a probe field, which interacts with this pattern.
Well, it doesn't have to be a probe. I mean, it has its own dynamics, which is...
Then the extra fields are present in addition, and they interact with this sector in a way which is determined by symmetry considerations, essentially.
Okay.
But even there was one small thing about massless fields which was a subtlety we didn't fully sort out. So I think it's just something.
I see. So you don't think it's going to ruin the Joukiffe-Teitelbaum part?
I don't think so.
Okay.
I don't think so.
So my second question is about this beyond S wave. I mean, I heard what you said, but intuitively this picture seems very odd because, unless maybe I'm just confused about the setup, RH over L means you have a huge S2 and a tiny, tiny little ADS2, and you decided to dimensionally reduce on the huge S2. Isn't that strange?
Well, so you could think I have so many modes.
Yeah.
Well,
and I mean mathematically it seems like you might get in trouble because even though what you were saying is true about each individual KK mode,
sum them.
You have almost a continuum of them approaching zero.
You have to sum them, yeah. So it's a matter of taking the low energy limit. So that's right. So let's say the S wave gave a contribution with scale like omega to the delta naught. This was the S wave. And then the next correction was omega to the delta 1, which is the, the next harmonic, and so on and so forth. Now, these are of order RH over L, say square. And so you have to go to suitably low energies. So I didn't make it precise. When the exact validity which I stated here was in the S wave sector, where it was enough to make omega to be less than mu.
Okay.
But when you actually include the higher partial waves, then the validity makes you go to even lower energies than this.
And there isn't a risk that in this limit you're working in, the energies you have to go to are so low that they even freeze out the interesting part of Joukiffe-Teitelbaum.
Yeah, okay, good question. So it turns out that actually for extremal systems, there's a well-known gap in the theory. And this was worked out actually quite a long time ago in a paper which I wrote with Wilczek and Preskel and Schwartz and so on, where the thermodynamics itself breaks down. But that temperature is even smaller than this. It's got a 1 over n square in it. And so you're safely above that gap. But you have to go to slightly absurd temperatures for the reason you said. But there is a well-defined regime where you then get this really universal theory, independent. That's what I expect.
So Sandeep, just to understand the statement correctly is that you compute this on-shell action with some sources turned on, and that is given by the same sources turned on for the S on the right-hand side. Is that correct? So you compute the action with boundary conditions that
Yes.
phi has to tend to the sources at phi C,
Right.
and it's exactly the same on-shell action. Is that correct?
Yes, it's exactly the same.
And the same sources.
This on-shell action we got
Yes.
is exactly reproduced by the Schwarzian down to every factor of 2. Actually, getting one factor of 2 took us about 3 months, but down to every factor.
And the mapping between the sources is trivial. It's the same source here and the same source here. How do you know that's not happening because of this limit mu L larger than 1? I mean, it's almost like the black hole that you have is taking up almost all of ADS. So this ADS4 region is almost kind of trivial, it's almost like this black hole is reaching the boundary.
Yeah.
How do you know it's not do you know that it's not happening because of...
The more general thing which probably is true is that there's some wave function renormalization. That there is that the source located at the ADS2 cross S2 boundary is related to the source you originally put in, okay, but by a factor which is independent of the precise endpoint correlator you look at.
Actually, I'm worried because somehow the intuition here was that when you go to low energies, the important part is coming from the ADS2 region, but it's almost like you're not using that intuition. Almost like you're forcing that to happen by just taking the ADS2 region to be almost all of ADS4. Isn't that? I'm worried that you're making this boundary approach almost close to the boundary of ADS. So this physical thing that you're looking for, which is that somehow it's near horizon dynamics that's important, is. It's going away because your black hole is so big.
The screen is located way down compared to asymptotic infinity. The lower the energy, the further down you can locate yours. The throat is actually infinite in length. So in the extremal system, the geometry looks, as you know, in terms of the radial distance from the horizon, it looks like this. And so the throat is really of infinite length. And you can locate this boundary. So there's infinite length between sort of the end of the throat and the boundary of ADS4. And you can locate the screen way down the throat for small enough energies. So it's nowhere near RH. Nowhere near the energy scale of the chemical potential. And that's when you get this universal.
I see. So I see. So you're saying...
It's not as if, you're basically working here, geometrically. You have the black hole, it's the asymptotic ADS4, you go way down.
I see. So then I'm a little confused. Why are you saying that this part between the screen and RH doesn't contribute at all? It just contributes 0 to the action.
Contact terms. Only, the kind of contact terms which plagued us the inflation work, there are sort of contact terms here.
Is just a delta function?
It is, I'll just show it to you, it factorizes into some function of R and a function of time. And
so you do have to smear the sources on the screen with that in order to get the proper ADS4 correlator still.
You may have to multiply the sources at the ADS2 screen by a suitable wave function renormalization factor.
Bulk boundary propagator.
Yes, the bulk boundary propagator.
From the screen to the
That's right, that's right. So it's a little, that's all I'm saying. So,
yeah.
But it's
this is very much in the spirit of semi-holography, where there's a relatively trivial propagation to the ADS2 screen. That's all. And then this is sort of the...
That's all it is. That's all it is. Sorry, I should have said it better. There's a bulk to boundary propagator. Okay, and then it's a little bit a matter of definition, whether you want to regard the source here, okay, let's put it like this. There's a bulk to boundary propagator, and then that determines what the source is here in terms of the source there, and then you can compute the correlator in terms of this source. But since it's so simple, you can just multiply that factor very easily, but that's what it is.
That factor is frequency dependent. It's not frequency independent.
It's frequency independent. That is why it's a universal factor, which is process independent. So let me just describe that very, very simply. The equation, if I look at box phi plus m square phi equal to 0, looks something like this. 1 upon square root of G dr square root of G G R R del R phi plus GTT omega square phi plus m square phi equal to 0. I might have some relative sign wrong. Okay, now what happens is that if your frequency is small enough, at the horizon, G upper TT goes to infinity, right? So the frequency can never be neglected because, you know, the frequencies get... But once you're sufficiently far away from the horizon, okay, for small enough frequencies especially, you can neglect this term. So... Yeah, the massless has some... I don't think it's deep, but allow me a small massive term, okay? Just allow me, that's why there's a bit of a subtlety. But, you know, you can neglect this all the way from the ADS2 screen out to the ADS4 screen, okay? And then what happens is, this is some function of R, which is because T has dropped out, frequency has dropped out. This is just some function of R. So that means the full solution is just this times e to the I omega t, or more generally, times whatever.
Sorry, but just to understand.
And this is the Basu boundary propagator analog, which is independent.
Understand, but that's because this guy with low frequency just doesn't propagate except in the near horizon region.
Yeah.
But the moment you go off, S waves and gravitons and so on will propagate everywhere. You know,
well,
you know, everything is trivial because it's not.
So these masses will go like 1 upon R square. Okay, and there are two effects. Okay, there are two effects. One is due to gravitons in intermediate states. Okay, those effects, okay, even in S wave, okay, all right, one is due to gravitons in intermediate states. Those effects, you can argue, quite generally, don't scale like RH cube. They scale like RH square. Okay, and then there are the effects due to the external probes themselves being not in S wave.
Just one last. Wave function renormalization factor goes exponentially with the depth of the screen. It looks like e to the minus m times RC. Is that correct? It's some e to the minus m times...
this one, right?
The wave function renormalization between the boundary and is it exponential in m?
So it's e to the minus m. Exponential will probably be, but I think in the very massive limit compared to L. That's correct. Please, please.
If you look at your effective action there on that,
yes.
So you have nicely demarcated the terms that you like to evaluate. Now, if you look at the last term,
yes,
that is a boundary term. That is root gamma, if I can see, phi at an extrinsic curvature
times the extrinsic curvature.
Correct. And the next term is also root gamma phi square extrinsic curvature. Now we know that the cutoff dependence actually cancels from the first term. So then what happens to the cutoff dependence in the second term?
Does
it go?
So this is why actually the way you do the near ADS2 calculation is subtle. And it is tied to what are the small parameters, or rather where is the screen being located. So let me put it like this. This screen, we have to locate sufficiently far from the deep infrared, but not too far into the ultraviolet. And that means the following, that since the basic scale for transition from the ultraviolet to the infrared is set by RH, the chemical potential, you have to locate the screen in these coordinates at R minus RH, which is sort of the ADS2 variable over RH being very much less than 1. Now, the dilaton does grow like this. This is your 1 over Z behavior, because Z, sorry to go between coordinates, but Z is like L square over R minus RH. Is the Poincaré Z coordinate. But you see, phi blows up in the sense that I say that R minus RH is going to become big, which means I'm going away from ADS2. But I can't go very far because I still have to work in a region where R minus RH over RH is very much less than 1. So the result is a term which goes like phi square, which is R. is still small compared to phi. So that's what suppresses the higher order terms in powers of 1 over RH. So you have to locate, because if you don't locate the screen sufficiently in the infrared, then you are just seeing the deviations away from ADS2. Once this quantity becomes of order 1, then you have to keep the full geometry. All the corrections are order 1. So the only sense in which the geometry is near ADS2 is if you have kept some correction, so that R minus RH, you have kept some corrections in this parameter, but the parameter is still small. That's what you have to do, and then you have to sort of carefully do that, and that's what makes, when you put it all in, and you see, that's what makes this term small. So yeah, so yeah.
Just one quick question. So sometimes these extremal black holes are unstable, even in the S wave, for let's say in the holographic superconductivity kind of setup. How do you see that in this framework?
Now, in those cases, is there a scalar which is below the bound or something?
Which is below the bound inside, but I mean in the ADS2, but not in the ADS4.
Yeah, okay. I mean, I haven't thought about that case. There could be such a scalar.
So if your scalar was charged, would it have followed the same analysis? You would have gotten a contribution from your gauge fields from the near horizon region?
Well, now you raise a question which is in very active discussion amongst us. As you know, there is also a Schwarzian type of analog of the Schwarzian type of action for a charge, for a phase degree of freedom that was written down by Sachdev and collaborators. And it's an interesting question how that could arise from bulk dynamics. Now, a very nice paper by Spenta has written in using 3D in Chern-Simons theory. They get that term. But you might ask, what about the more general setting? And okay, till now we don't see the mode. I'm almost willing to say that the mode doesn't exist, except a very distinguished lecturer who spoke last week almost beat us up about it. So we don't see the mode. So if that's the case, this would be the whole dynamics. So far, we don't see the mode at all.
Okay, so then we'll break for tea, and we can be back by in half an hour, 11:30 maybe.